Welcome to the field-oriented control of an induction motor drive by using Simulink course. Are you ready to embark on a journey into the electrifying world of advanced motor control techniques? This comprehensive course offers an in-depth understanding of how to design, simulate, and implement field-oriented control (FOC) for induction motors, giving you the hands-on experience you need to excel in the field. Your instructor is a seasoned automotive electronics senior hardware design engineer with over 14 years of professional experience in vehicle electrics, electronics, and power electronics. With specialized knowledge in robust design, safety analysis, and hardware architecture, your instructor brings a wealth of practical insight into this course. Course structure will be as you can see. Fundamentals of controller design techniques, pulse width modulation with space vector PWM, space vector analysis and vector control, control-oriented modeling of induction machines, control design, and Simulink simulation of induction motor drives. The electromagnetic torque is proportional to the product of gap field and armature current. In separately excited DC motor, the orthogonality is maintained between the armature and field currents with the aid of the brush and commutator, and the field current and the armature current are controlled independently. The field-oriented control, often called the vector control, refers to all AC machine control methods that split the current vector into flux and torque components and control each of them independently. The basic control principle is the same as that of DC machine, except the rotating reference frame. The phase currents are transformed into a synchronous reference frame, whose d-axis is aligned with a flux vector. The d-axis current determines the flux magnitude, whereas the q-axis current, being orthogonal to the d-axis, controls the torque. In the case of induction machine, the control methods are sorted as rotor, stator, and air gap flux-oriented schemes, depending on the flux on which the frame is referenced. Among them, the rotor-flux-oriented scheme is most popular for simplicity and good decoupling nature. A technical hurdle is the difficulty in measuring or estimating the flux angle. Based on the flux angle access methods, field-oriented controls are categorized as direct and indirect methods. The direct field-oriented control relies on the flux estimates or measurements. The flux can be measured by using flux sensing coils or Hall devices. But the flux measurement is rarely used in practice since it is not easy to install a sensing device in the air gap or slot, and the signal processing circuitry adds an extra cost. Usually, flux is estimated by utilizing flux observers. On the other hand, the flux angle is estimated by integrating the sum of calculated slip and measured rotor speed in the indirect field-oriented control. Sensorless control is a collective term of field-oriented control methods that do not utilize speed or position sensors. The vector control without a speed sensor is attractive in the practical application, since it eliminates many problems in sensor installation, cabling, processing circuit, and low signal-to-noise ratio. Enhancing the torque and speed performance in the low-speed region is an ongoing problem in the sensorless control. In the automotive industry, the control of PMSM and induction motors without sensors has not yet been extensively adopted in series production. The primary reason for this reluctance revolves around concerns related to safety and system reliability. The intricacies and variables in sensorless control can lead to potential inaccuracies or unexpected behaviors, which, in the context of the automotive sector, could translate to significant safety risks. Vector control, which utilizes sensors, remains the prevalent approach as it offers more precise and predictable motor behavior. By leveraging sensors, the system can acquire direct and real-time feedback, ensuring a consistent and dependable response, especially under varying load conditions and external disturbances. As the industry continues to evolve, there's ongoing research into refining sensorless techniques to meet the rigorous standards required for automotive applications. However, until there's a breakthrough that guarantees the same level of reliability and safety as sensor-based solutions. The latter will remain the standard choice for many manufacturers. Who is this course for? Engineers looking to understand and implement FOC in induction motors, students studying electrical engineering, researchers focusing on electric motor control, anyone who is interested in mastering control algorithms for electric drives. Enroll now and take your career to the next level with our groundbreaking course on field-oriented control of an induction motor drive by using Simulink.